Thank you. In the next 20 minutes, maybe 25 minutes, I will talk about the development of computational strategies for environmental chemistry. So the talk is organized as follows. After a brief introduction, talking about basically environmental pollution and the role played by trace gas pollutants, we will also highlight the need for a spectroscopic characterization of pollutants as well as of their reactivity mainly in the atmosphere, and we will highlight the role of computational chemistry in this field. Then in the first part, I will treat the simulation of spectroscopic properties and the reactivity of molecules, mostly halogenated organic pollutants in the gas phase. And then in the second part, I will move to the condensate phase, presenting some results we obtained for, let's say, ice-mediated chemistry. So let me give a description of the framework in which we move, basically our motivations. We know that in addition to the main atmospheric components, the atmosphere contains plenty of trace gases whose concentration is lower than 1 part per billion. However, their role is not commensurate to this low atmospheric concentration. Indeed, they are responsible for several climate and environmental impacts. In particular, anthropogenic activities have a huge impact on the atmospheric composition, both altering the mixing ratios of naturally occurring gases and releasing new substances. Mostly of them hazardous in the sense that they contribute to global warming, or they can also be ozone depleting chemicals. And all of this during the years caused many problems like photochemical smog, acid rains, the ozone hole in the mid of the 80s, global warming, and all these factors at the end contribute to climate change. And the climate change studies need, first of all, to monitor the concentration of the atmospheric gases, in particular greenhouse and ozone depleting gases. And this is done nowadays thanks to the use of remote sensing spectroscopic techniques by means of the instrumentation mounted on board of, let's say, satellites or even ground or airborne based observatories. Among all the spectroscopic techniques, IR spectroscopy is particularly well suited because in practice almost all the atmospheric components, but most important, the atmospheric pollutants present strong vibrational rotational bands in the IR spectral domain. The second aspect that we need to consider is the reactivity, or better, the degradation mechanisms of the pollutants once introduced in the atmosphere, and we need to understand this in order to know how rapidly these substances degrade, when and where they are destroyed. This is strictly related to the atmospheric lifetimes, and something that sometimes is overlooked, but it's actually very important. Understand if the degradation products can lead to worse chemicals than the parent species. Okay, so we have two aspects to consider. One is spectroscopy, the other is reactivity. And to exploit the observational data obtained by means of remote sensing techniques, we need first of all to accurately characterize the spectroscopic properties of the relevant molecules. This is usually done through laboratory experiments. Indeed, the main aim of laboratory molecular spectroscopy is to provide the spectroscopic data for the target species. However, this task is almost always complicated by a number of factors. Let's say, for example, the presence of conformers or the necessity to synthesize in situ unstable species, or even intrinsic properties of the molecules like resonances that at the end alter the spectral structure, thus making the interpretation really difficult. On the other hand, concerning the reactivity, we need to understand the reaction of the pollutants toward the main atmospheric oxidants. The most important is obviously the OH radical, but also the NO3 radical, chlorine, or even molecular oxygen. However, here the experimental approach must consider a large number of compounds and the large number, the reaction they give rise. Therefore, the experimental approach is very often a daunting task. And for this reason, measurements, experimental measurements, are increasingly supported by computational simulations for both spectroscopy and reactivity, and these simulations actually helps in the analysis of the experimental outcomes, and sometimes can be used directly to interpret the observational data. So let me enter therefore in the first part. As I said before, we need to consider both spectroscopy and reactivity. From the point of view of spectroscopy, for computational approaches to be useful, they must fulfill strict accuracy requirements in the prediction of the spectroscopic properties, and in particular, I refer to transition frequencies and intensities. The ideal target is the so-called spectroscopic accuracy. In practice, the ability of predicting transition frequencies with an accuracy of 1 wave number. Actually, this nowadays can be done only for very small molecules, let's say composed by 3 or 4 atoms. And therefore, in the other cases, we are pretty much happy if we can reach an accuracy within 5 wave numbers. On the other hand, for concerning reactivity, the accuracy requirement is the so-called chemical accuracy for reaction energies and reaction barriers. That is to say, an accuracy of 1 kcal over mole. But even better is if we can reach a subchemical accuracy. And ideally, the computational protocol should be the same, or at least very similar, both for spectroscopy and reactivity. So what are the ingredients of our recipe to achieve the targeted accuracies? The first requirement is an accurate geometry. However, today I will not go into the details of this aspect because it's a quite long discussion, and I move to the second requirement. The second requirement is the ability to go beyond the harmonic approximation. This is true for spectroscopy, but in practice it is also true for reactivity, because anharmonicity enters in the 0-point vibrational correction to the energies, and therefore we need to account it for both spectroscopy and reactivity. Our approach to introduce anharmonicity is based on the use on vibrational perturbation to vibration perturbation theory to second order. Basically, it starts from the full row vibrational Hamiltonian, and it expands in a Taylor series some elements. In particular, the potential energy is expanded in a Taylor series as a function of the nuclear coordinates, and this allows us to introduce anharmonicity in transition frequencies. We need also to introduce anharmonic effects in intensities, and for the purpose that the components of the molecular dipole moment are expanded in a similar Taylor series. And then perturbation theory is applied on the expanded Hamiltonian, thus achieving the usual expression for the transition frequencies, here expressed in terms of the vibrational term value V, which in practice is composed by two terms. The first one is the harmonic contribution, whereas anharmonic contributions, anharmonic effects are accounted for by the anharmonicity constants. I don't want to go into the details of these equations. I just limit myself to say that there are some issues related to resonances, but let's go ahead. Therefore, we say that we need accurate geometries, a method to treat anharmonic effects, and then we need an accurate level of theory. Accurate level of theory in quantum chemistry is synonymous of coupled cluster theory. However, for our purposes, a full anharmonic calculations at the coupled cluster theory can be too demanding from the computational point of view, and I have to say that it is even not necessary. And furthermore, for what concerns the prediction of reaction energies, coupled cluster theory alone cannot give the proper accuracy requirement. For this reason, we use composite schemes. Basically, in composite schemes, the target quantity is subdivided in the different contributions, and each contribution is then treated at a proper level of theory, and then the different contributions are again summed together to give the best estimate of the target quantity. On the other hand, to save computational time, we also resort to hybrid coupled cluster, or better, composite schemes density functional theory approaches, in which in practice the harmonic properties or electronic energies evaluated through composite schemes are mixed with anharmonic contributions or vibrational or zero-point vibrational energies evaluated by means of density functional theory, thus achieving a saving in the computational time. These are the details of our computational protocols. I don't go into their details, into their detailed description. Clearly, I will be happy to answer questions about it. I just wanted to focus on the accuracy we can reach. By using our methods, we can reach an accuracy within 5 with numbers for the prediction of transition frequencies, and an average accuracy of 5 with numbers for the prediction of transition frequencies, and all transition frequencies are predicted within 10 with numbers. On the other hand, for what concerns the prediction of reaction energies and barriers, we can achieve a subchemical accuracy. And actually, we are applying these computational strategies to understand and to simulate the spectroscopic properties, as well as the degradation reaction mechanisms of a family of compounds called the hydrofluoroolefins. Actually, why the interest in hydrofluoroolefins? Basically, because we are currently living a transition from hydrofluorocarbons Actually, hydrofluorocarbons were introduced, let's say, in the 90s as a replacement for the chlorofluorocarbons as a consequence of the Montreal Protocol. But nowadays, the new regulations that aim at achieving a reduced global warming are planning to replace hydrofluorocarbons with other molecules that have a lower impact on the global warming point of view. And one such families of compounds are the so-called very short-lived substances, and hydrofluoroolefins belong to this family. In particular, some years ago, trifluoroethene has been proposed as a refrigerant of the new generation, and for this reason we decided to explore and understand its spectroscopic properties, in particular in the infrared region, and also its reactivity. This is the result of an integrated theoretical and experimental study in which the experimental spectrum of the molecule has been investigated in the 205,000 wave number region. Here we have in practice interpreted the vibrational structure and determined the absorption cross sections, and this characterization has been driven by our experimental calculations of geometry as well as the spectroscopic rotational properties. Here there is a survey of the infrared spectrum together with the comparison between experiment and theory, and actually we can see that all the fundamental transition frequencies are indeed predicted with an accuracy within 5 wave numbers, in particular with a mean absolute error of 2.6 wave numbers. And then we also evaluated then the global warming potential of this molecule. Now we are investigating its degradation mechanisms, starting with the reaction toward the OH radical. Here actually two channels are open. The first one is the abstraction of this hydrogen atom by means of the OH radical with formation of this fluorinated radical and water, but the most interesting pathway is related to the addition of the OH radical to the carbon-carbon double bond, and here we need to address the radioselectivity issue, because the OH radical can add either to the carbon atom of the CF2 group and to the carbon atom of the CFH group. Actually, we have explored all the reaction pathway. You can see here the mechanisms. We have identified this, let's say, the stable products and the energies are here reported of intermediates, and transition states are here reported within parentheses. Let me move now to the second topic related to the processes occurring in the condensed phase. Here we focused in particular on the processes taking place on the ice surfaces, because actually the ice-mediated chemistry can have a huge impact on the chemistry of the atmosphere. And here probably the most important example comes from the explanation of the ozone hole in the Antarctic. Indeed, the extent of the ozone hole in Antarctica wasn't explainable by considering only a gas phase reactivity, but rather it was explained by considering the processes occurring on the icy particles contained in the polar stratospheric clouds. Actually, these icy particles can catalyze the reaction here reported between chlorine, nitrate, and HCl with the formation of nitric acid and molecular chlorine. Then, during the Antarctic spring, with the rising temperature, chlorine is released again in the atmosphere, and then it undergoes homolytic dissociation because of the UV radiation from the sun, and the chlorine atoms formed in this way catalytically destroy the ozone layer, and this resulted in an enhancement in the depletion of the ozone layer in the Antarctic. From this example, you understand that we need to explore the mechanisms of the reactions taking place on cloud ice in order also to understand their effects on the chemistry of the troposphere or the upper, of the stratosphere or the upper troposphere. And from this point of view, computational chemistry can provide the atomistic details of the reaction mechanism. Here, however, we need to consider the interaction between a molecule, let's say an atmospheric constituent or an atmospheric pollutant, and the ice. And this means that we need to treat an extended substrate, and for this reason we need to forget coupled cluster theory and the composite schemes I presented during the first part, and we need to resort to density functional theory in moving in a framework where we have a plethora of density functionals, and each is presented as the best performer over all the others. For this reason, we decided, first of all, to make a benchmark study about the performances of the different density functionals in simulating ice-mediated chemistry. Actually, I have to say that this topic is not new, but it has never been treated in a systematic way. For this reason, we considered a paradigmatic reaction, the HCN to H and C isomerization reaction, and we considered a number of density functionals chosen on, let's say, on the basis of our previous knowledge. And we benchmarked their performances in predicting not only reaction energies and barriers, but also geometries. In order to do this, we have employed a small model system composed by HCN in interaction with a dimer, a water dimer. Why this simplified system? Because it is small enough to be treated through the composite schemes I presented in the first part, which therefore have been used to generate reference values for geometries and reaction energies and barriers, and the predictions from the different density functional theory methods have been assessed through comparison of to these accurate values. The results obtained that are here reported. I don't want to go into the fine details, but let me say that in practice we have been able to identify in a sense, a higher level of theory among the density functionals that we have considered, but with also a higher computational cost. On the other hand, we have also been able to identify a more approximate method, but with a lower computational cost. And these two have been used then to scale up the size of the system simulated. We have considered the same reaction, this time occurring on a cluster composed by 20 water molecules. Here, the reaction center that is composed by the HCN molecule and the 4 water molecules that are involved in the in the transfer of the hydrogen from one side to the other of the molecule have been treated with the higher level theory, whereas the remaining 16 molecules have been treated with the more approximate method. And here in the graph on the right is presented the energy profile of the isomerization reaction simulated to be mediated both by the water dimer or the cluster composed by 20 water molecules. The dimer results are in red, those obtained on the 20 water molecules cluster are reported in black. We can see that all the species are stabilized by the presence of the 20 water molecule cluster, but what is most important is the reduction in the energy of the transition state, meaning that on the cluster we have a lower reaction barrier, and therefore the cluster actually behaves as a catalytic surface. And furthermore, these results show that in order to properly simulate reactivity on the ice surface, but on the surfaces in general, we need to consider an extended surface, and a simplified model is not enough to guarantee correct results. We also scaled up further the size of the system by moving to a substrate composed by almost 200 water molecules, but in this case the results obtained were essentially unchanged with respect to those obtained on the 20 water molecules cluster. And then from the thermochemical parameters, we computed the kinetics of the reaction, again on mediated by the water dimer and on the cluster composed by 20 water molecules. You can see by comparing these graphs that actually the reaction proceeds faster by several orders of magnitude on the cluster. And furthermore, the kinetics has been simulated by considering quantum tunneling in A and C, and neglecting quantum tunneling in B and D. And actually, by comparing results with quantum tunneling against those without quantum tunneling, we can see that actually the inclusion of tunneling effects increases again the rate constants by orders of magnitude. I just mentioned that we are now working on modeling the spectroscopic properties of molecules adsorbed on the ice. And here what we aim to do is to set up an hybrid approach, in the sense periodic cluster approach, in which results for, let's say, harmonic frequencies from an approach using periodic boundary conditions are mixed with anharmonic contributions evaluated in the framework of the cluster approach, and this allows one to use molecular codes and the implementation of anharmonic calculations. I skip the results. The results are about almost encouraging. There are something that need to be still fixed, and therefore with this I have concluded. I want to thank Professor Barone that contributed to some of these results, but I want mostly to thank my close collaborators that performed the works I presented you today, in particular Georgia, who is doing gas phase spectroscopy, Zoe and Najib that are working on gas phase reactivity, and Carmen that takes care of the processes occurring on the ice surface. I want also to thank the collaboration with the experimental group in Venice, and clearly thank you for the attention.